Oh, yeah. All right, so let's get started. So this is the review session for machine learning. If you're here for Russian literature, then you might want to leave now. Here's the let's make this big. So here is the here are the topics. Everybody read those? Should I make them bigger? There, that's pretty good. So the way this is going to work is this is driven by your questions. So you ask me questions about things that might or might not be on the exam, and I'll do my best to answer. So who wants to start off? Yeah.
In the recitation yesterday, talking about kernels, there's a question about quadratic kernels.
Yep.
Quadratic kernel will introduce quadratic decision boundaries.
Yep.
In one of the presentation, one of Alex's presentations, he just used the analogy of kernel there were like circular decision boundaries.
Right. Oh, so that's what a quadratic decision boundary means. Essentially a conic section, right? So you can make a hyperbola, a parabola, a circle, an ellipse, right? So a quadratic decision boundary means a level set of a quadratic function.
Are kernels kernels? Are there specific types that we should know more about?
Let's see. So the specific kernels that we mentioned a bunch of times are the Gaussian RBF and all of the polynomial ones, and then of course the linear one. Those are the main ones you'd need to know about. There's, for general use, it's good to know about a few that are not for, vector spaces that are for things like strings or trees or other structures, right? Just know that they exist and that you can look them up if you need to. Anybody else? So I take it you're all going to ace the midterm then? You have no questions left? Yeah.
Sorry, actually, just to go into that a little bit more.
Yeah.
So for instance, if you have like a quadratic kernel, you could end up having any of those conic types of sections as decision boundaries. Is that correct?
Yeah, that's right.
Okay. Okay.
And then in general for other kernels, right, the sorts of things you can get are the level sets of functions you can represent with those kernels. And what I mean by a function you can represent with a kernel, let's see, is this going to work? Helps if I turn it on, probably. Yeah, there you go. Right, so you have a kernel, right, k of x and x prime, right? And the sort of thing that you can represent, your decision function is going to be sum over I of alpha I k of xi comma dot, right? So this is the function which you get by fixing one argument of the kernel. And so this is the sort of decision function you can get. And then decision boundaries are going to be what you get when you say that this is greater than or equal to b, right? So that's the level set of a function, right? And so, for example, if you have Gaussian bumps, well, I could put a point here, a point here, a point here, and then they have equal weight plus 1, right? Then the level set's going to be, something like this. The drawing's pretty bad, but it's going to be, right, you have these Gaussian bumps and something that's pretty near each of these three things, right? And so this will be, let's say, positive, and that'll be negative. Yeah.
How would that data look for multiple classes?
Right. So with multiple classes, you would wind up having one of these guys, right, a decision function for each class, and you would choose the class that had the largest value of the decision function, right? And so, think about the sort of thing that you can get by taking a bunch of these smooth functions and then taking the max of them, right? And then looking at where each one, where the kth one is maximal, that's where the kth class is going to be. So anything more about support vector machines? There's a bunch of cool stuff about support vector machines to know, right? And I'm sure there's nobody in the world who knows all of it, although all of it won't be on the exams. So.
So in a support vector machine, and in dual problem, and you have so alpha I contains from 0 and c.
Mm-hmm.
And when you increase the c, you have better classification. So I think
when you increase this, so the question is, when you increase the C in a support vector machine,
yes,
you will have better classification of the training set, right? Not necessarily of the test set.
okay. So from the pictures he showed us, seems that the bigger the C, the better the classification
Of the training set, right? So if you increase C, you penalize yourself more for for making errors on your training set. There's no penalty, right, in the optimization for making errors on your test set because you don't know your test examples. So it would be great to put in such a penalty, but it's very hard to implement it because you don't know your test examples.
Yeah, so how would you choose the optimal C?
How do you choose the optimal C? Right. So that's a perennial question for support vector machines. So a couple of answers, right? So the first answer is cross-validation, right? So you try a range of C's on some, let's say, 2/3 of your training set and see how well they classify the remaining third. And so if you choose C too large, your decision function is going to work too hard to fit your training set. And so it'll give you a crazy looking decision boundary that's not going to generalize well. And it won't do well on your test set. If you make C too small, it's going to be like, training set errors, who cares, right? And so it'll give you something that's way too smooth and won't generalize well. And if you pick the Goldilocks value of C, you'll get a decision boundary that generalizes best. So too big or too small is bad, and what you should do is try a range of values in a cross-validation, right? That's the practical answer. And then today, Alex was talking about the new trick, right, which is this new was the expected fraction of errors on the training set. And it gives you essentially the same knob to play with that C does, except that it's much more interpretable to say, I think this is pretty noisy data. Maybe I only expect to be able to get 80% right on the training set. Or I think this is very clean data. I should be able to get 99.5% on the training set, right? And it's sort of, in both cases, it's how hard do you work to classify the training set, making these little, divots and strange curves in the decision boundary, right? Yeah.
Do we need to understand how to prove the convergence of a bound of algorithms, something like this?
Do you need to understand how to prove the convergence of algorithms? I think we only covered convergence for one algorithm, right, which was the perceptron.
No, gradient descent.
Oh, gradient descent. Yep, we covered it for gradient descent as well. So yeah, you should understand those proofs. It would probably be too long a question to ask you to do a complete convergence proof for an algorithm, so we might ask you some portion of one of those proofs. But, right, so give you like a lemma, right, to prove that's, related to it. Right? Or ask you, something qualitative about one of the proofs, right? Like, for stochastic gradient descent, right, there's, well, let's take Perceptron as an example, right? So there was this idea of a potential function in the proof, right? And there were you were trading off errors that you made against improvements in the potential function. So we might ask you, like, how do you use a potential function in a proof, right? Or what's, give you like some lemma about how a potential function changes and ask you to prove something based on that. Yeah.
In the second homework, we had a question which involved the whitening of data.
Which involved whitening of data, yeah?
Could you talk a little more about why would be, I mean, it seems that you whiten data because you want to get rid of the correlation between different features?
Right. Whitening data means getting rid of the correlation between different features.
One is how do we do it?
Mm-hmm.
Two, why do we do it?
So how do we do it and why do we do it? Yes. Good questions. So how do we do it? So it depends on the dimensionality of the data. If the data is low dimensional compared to the number of samples you have, you can estimate the covariance of your data, right, using the samples, right, and it'll be a pretty accurate estimate. And so what you can do then is multiply by the inverse square root of the covariance, right? So pretend the data is centered, right? So suppose E of x is equal to 0, right? So then the covariance is E of x transpose, right? And so I said to take the square root of that, right? So that just means we take a factorization, call it L transpose, right? So the covariance is equal to L times L transpose for some matrix L. So then if we take y is equal to L inverse x, right, then E of y transpose is equal to E of L inverse x transpose, which is x transpose L inverse transpose, right? So if I transpose L inverse x, I get x transpose L inverse transpose, right? And so this is then y transpose, right? This here is y, and that is y transpose, right? Then expectations are linear, so you get L inverse E of x transpose L inverse transpose. This here we know is L transpose, right? So this L inverse cancels that L inverse transpose cancels that. You get the identity, right? So this specific, we didn't teach you, by the way, this specific way of whitening, but that's the answer to your question, is this is how you would whiten data.
So L is the covariance.
The covariance is L transpose, right? So we'll call that sigma for the covariance, right? And so L transpose is just a factorization of the covariance, right? So this is what I mean by the matrix square root, right? So
When you multiply that with the data, you get y.
right, and so if you take this square root and you multiply by the inverse square root, you get y, right? And I just showed that the covariance of y is the identity, so I've succeeded in whitening my data, right? Yeah.
So can you always do that?
So as long as the covariance is full rank, right? If it's not full rank, then you can't do this inverse. But as long as the covariance, as long as the sigma here is full rank, then you'll be able to, then L will be full rank because LL transpose, right? If L is low rank, then sigma couldn't possibly be full rank. So if sigma is full rank, L is full rank, L inverse exists, and all of this works.
So, no, I mean, X is the input and Y is the output.
No, sorry, Y is just the transformed whitened X. So maybe I should have called it something other than Y.
Okay, so X is the original and Y is the whitened.
Y is the new whitened input, that's right. And then there might be labels somewhere which I'll call Z or something, right? So this is just, whitening is a property of the input variables, right?
So there are multiple choices, so
There are multiple choices of L, and they'll all lead to whitened data. So a good choice, a good efficient choice is the Cholesky factorization, right? Another choice, you can do it using the singular value decomposition, right? So that's how, right? Oh, that's half of how, because I said this is how you do it for low-dimensional data. For high-dimensional data, what you would do is you would take the empirical covariance and add lambda times the identity to it, right? So you do like a ridge term on the covariance and then go and do the same thing, right? And the reason that's important is that for high-dimensional data, you won't have a very accurate estimate of the covariance. And so when you do this inverse, it could be poorly conditioned. And adding lambda I makes it better conditioned.
What do you mean by
Poorly conditioned means that the ratio between the largest and the smallest eigenvalue of sigma is bad, meaning largest over smallest is big. Right, so if you had one eigenvalue that was 10,000 and another that was 10 to the minus 3, right, then you'd have 10 to the 7 as the ratio. That's not so great.
So that means there's a problem with the data?
Well, that just means you don't. No. It means that your data started out very non-white, right? Or there's a problem with your estimate of the covariance, right? And so if you have small amounts of data, if you have small dimensionality, right, but a lot of data, then you'll have a very accurate estimate of the covariance, and you'll be sure that you started out with far from white data, and you'll need to do something drastic to it, right, multiply by this big number in order to make it white. If you had high-dimensional data, then probably the poor conditioning resulted from having too small a sample size, and so you want to do something not drastic, which is why you have this lambda term, right? This lambda term, right, so just like 1 over x, the slope is crazy near the origin, right? So you add something to it, move away from the origin. You don't do something drastic, right? It's the same thing here. So, but this is more just in the spirit of answering your question, right? So we didn't teach you how to whiten data, and so I'm not planning on putting that on, question about how to do it on the exam. Why do you whiten data? That's a good question. So for a lot of algorithms, the convergence rate depends on how well conditioned the problem is. And so whitening your input data is one way to make the problem better conditioned and therefore get faster convergence. It's not the only way, and also it's not even necessarily a good way, right? Like if you start out in some ridiculously high-dimensional space, it might be so expensive to whiten the data that you lose all of the time in whitening it that you save later for faster convergence. But in general, whitening can speed up convergence. Another thing that whitening can do is simplify an algorithm later. So for example, we haven't done independent components analysis, but if you do independent components analysis, one thing that you often do is whiten the data first so that the derivation of the rest of the algorithm is simpler. Yeah?
So when would we not want to whiten data?
When would you not want to whiten data? When it's too expensive, or when you can't get a good estimate of the empirical covariance matrix, right? So it could be, if your algorithm doesn't require whitened data and you have, so many variables that you have only a bad estimate of the covariance, then multiplying by the inverse of a bad estimate is usually a bad idea. Yeah.
Does midterm cover this week's series?
So the stuff on, so the midterm covers the topics that I put up, right? So we mostly didn't talk about those topics, right? Here are the topics. We mostly finished talking about those topics before, right? I'm not saying you won't learn anything about the midterm, right? So we told you stuff about kernels. Kernels are useful. We're not specifically going to try and ask stuff about this most recent week, but I'm not going to say that we never mentioned in this most recent week anything related to any topic that could ever be on the midterm, right? That would be too strong, right? So it's about these topics, right? And you can learn about these topics from any way you want, and we mostly covered these topics in lectures before this past week.
Are you going to cover risk minimization, like loss function and stuff like that?
Yeah, so the idea of empirical risk minimization was the basis for a bunch of the algorithms we discussed, right? Things like the Perceptron or the support vector machine. You can think of linear regression that way. So the idea of risk minimization is definitely pretty central Types of loss functions, you mean like squared loss or hinge loss? Yeah, those are pretty useful to know. I can't tell you exactly what's going to be on the test, but I would imagine that a hinge loss has some chance of appearing, right? A squared loss has some chance of appearing. Well, I don't have them, so I can't personally, but I'll let Alex know that that you guys would like them up. So yeah, I mean, I think the goal is to have them up soon. I'm actually surprised that they're not up already, because usually he's pretty good about getting them up.
So in past years, what has been the least understood topic that prone students to make errors on?
Huh. That's a good question. If I knew that, I would. So the question was, in previous years, what was the most misunderstood or most error-prone topic? So that's a good answer. A good question. So let's see if I can give a good answer. So there are a few of them, right? So I mean, Lagrange multipliers and duality, people often have trouble understanding, right? The kernel trick, people often seem to have trouble understanding. I'm guessing there might be a few people in here in that boat. So push that on the stack. Ask me some questions about the kernel trick in a sec. So that's your professor rebooting. You know, there are, I would say, I mean, there's scattered errors in every topic, right? It's not like, you know, nobody missed any of the other ones. But I would say that, actually, another one that seems to cause problems is English language statements into mathematical statements about probability. Right, so you remember the homeworks about the Monty Hall problem or about the servers, right? And there were, you know, this skill of taking a qualitative description of a problem and turning it into a quantitative one. It's important, and we might test it, right? So, right, so I got a bunch of. They agreed with that it was hard. Yes. So, so what can I tell you about the kernel trick? Right. So name a situation where you would rather use a kernel method than the original primal method. Right, so what's going to happen, right? So when you do the kernel trick, right? So you did the, you re-expressed your algorithm in terms of dot products between data points, right? And so the situation where that's going to be expensive is when you have a lot of data points, right? So on the other hand, your original algorithm, right? So that was in terms of the weight vector and the feature vectors, right? So when's that going to be expensive? When the weight vector and the feature vectors are very big, right? So if you have, so for example, take the perceptron versus the kernel perceptron, right? If you have billion-dimensional feature vectors and 100 examples, right? It's going to be much, much cheaper to make a 100 by 100 gram matrix, kernel matrix, than it is going to be to go through even one training example, right? On the other, the opposite way, if you have a billion training examples and a 100 by 100 feature, 100 length feature vector, right? Then doing stochastic gradient on length 100 feature vectors, you may not ever even have to touch all your billion examples, right? So that would be a good example of when you prefer one versus the other. Yeah.
On the homework, it asks for how many floating point numbers are needed to store things when you're using the kernelized version.
Right.
I definitely would like wave my hands all over that answer. So is there a better way to answer that?
So just you think about all the quantities you're storing, right? So you're going to store. So I'm sorry. What was it? Remind me what you were asking about storing. Was it the weight vector? Right. So the trained model and the non-kernelized version. What's in the trained model and the non-kernelized version? I mean, the weight vector is in the trained model, and the intercept is in the trained model, right? So how big is the weight vector? You know, it's n by 1, where n is the number of features, right? So you have n plus 1 floating point numbers to store, right? Plus the b. Right? I don't remember whether the homework question asked about the b or not, whether there was a b in the... No, the intercept is optional. That's why it's either n or n plus 1. The problem presumably stated whether there was an intercept or not. I don't remember what it said. There was no intercept. Okay, yeah. Yes, but then you have to make the weight vector longer by 1, so the number of floating point numbers is the same, right? So that's right. So you think about like what does the trained model contain, right? So in the primal problem, the trained model is a vector of weights and possibly an intercept, depending on like if the problem said that your decision function was w dot x, then there's no intercept. If it said it was w dot x plus b, then there was an intercept, right? So it's either n or n plus 1. With the dual, right? What do you need to store? You need to store the you need to store the alphas. What? And the training data, right? And so you need, and so you know, you just count how big those are, and that's how you get the answer. So, more about kernel methods? Yeah. Yeah. So, problem on Lagrange multipliers or duality. Let's bring this closer. Sorry, is someone asking a question this way? Was on ridge regression? Kernel, was it kernel ridge regression? Okay. I think I answered for like a perceptron instead of a ridge regression, but the principle's the same, right? So your trained model is in the primal, it's the weight vector. And in the dual, it's the Lagrange multipliers, right? Plus your training data. And so you know, how many numbers? All right, so work out something. So, I mean, one simple thing that we might ask you to do is to take a dual of some simple problem, right? So let's do that. Sure.
So it's asking how many floating point numbers are needed to store the kernelized and non-kernelized. So you mean they're the same? Because it's just dot product, right?
No, the kernelized and the non-kernelized will in general need different numbers. And so the problem was asking you to answer twice, once for the kernelized and once for the primal non-kernelized version.
And you said you just count the number of features and they are the n feature is the same.
So in both cases, right, you had a trained model, which was represented somewhere in the program, right? If you wrote a program, there'd be variables that stored stuff that let you do classification later. And it's asking you to count how many memory locations you're using to store all of the variables that you need later to do classification.
So they are different.
In general, for kernelized and non-kernelized, you'll need different amounts of storage and different amounts of runtime as well. Yeah.
I'm not sure this is what people may be confused about, but the number of features that the primal is trained on, like there's a difference between the number of the dimensionality of the input data and the number of features we decide to take over that data, right?
That's true. So the question was, what if there's a difference between the dimensionality of the input data and the dimensionality of the feature vector, right? And you could answer for both cases, right? So you could answer for the identity feature map, in which case those two things are the same. Or if the feature map is not the identity, you could answer for, let's say you take a feature map that is, let's say your data has 100 features, but you take a feature map that's length 1,000, right? Then in the primal model, you're going to need weights. How many weights, right?
Currently, I think that's 1,000.
1,000, that's right. So you can answer in both cases, right? And if the midterm isn't clear about which case, raise your hand and ask us, right? But hopefully we will have gotten rid of any lack of clarity in the midterm.
On the homework, it seems like they were the same, and so you have 1,000 versus 1,000 times 1 plus, the number of training points you have. So kernel method
Didn't look that attractive. Yeah, I don't remember what the exact setup was, right? But if you picked the kernel method is going to be most attractive if you pick a feature vector that's very long, right, compared to the primal, right? Because then you're not going to, in the dual, you store only the original examples, right? You don't store phi of x, you store x. Right, and so if it's 100, if it's 100 features in x and 1,000 features in phi of x, you'll get 100 times the number of training examples, plus the weights, which is the number of training examples, the Lagrange multipliers, right? And so if you change the length of phi of x, you can make either the primal or the dual seem more attractive. All right, so I was going to do something related to Lagrange multipliers. So I could say, for example, here's a linear program, minimize 2x plus y subject to, I don't know, x and y are both greater than or equal to 0. X plus y is greater than or equal to 1, right? This is a nice small linear program. Should be able to take the dual, here on this one slide. So yeah, and so so we'll consider this to be a program in inequality form. So we'll get a standard form program as the dual. So we'll introduce a Lagrange multiplier, right? So we'll call them. There are 3 constraints here, right? We'll call the Lagrange multipliers A, B, and C, right? They're all inequality constraints. So we get A, B, C are greater than or equal to 0, right? And then you can do this we showed you 2 different ways to do this, right? We showed you how to do it as thinking of trying to get a lower bound on the optimal value, or as making a Lagrangian and differentiating it. So let's do it the second way. So the Lagrangian is going to be 2x plus y, and then we're going to have a times the first constraint, which is x, right? We're going to have b times y, right? B times the second constraint, and then c times x plus y, right? And the sign of this, so since this is a minimization problem, what we're going to want to do is make it so that when a is positive, we're going to want to make x equal to 0. So it'll be like that, and that, right? No, I got it wrong. Let's let me, right? So if x is less than 0, right, then right. So right, yeah, we want it like this. So if the way you tell, you look at, suppose the constraint is violated, right? So suppose x is less than 0, then you want the max player who's controlling the Lagrange multipliers to be able to win, right? Push the value of the Lagrangian as high as possible, right? So then if x is negative, minus x is positive. So a times minus x, when a is positive, will be able to be as high as possible, right? So that's how you get this, right? So that's, and then same for all of these.
Should it be minus
Yes, thank you. This is what I get for writing out the problem with no prep. Yes, x plus y minus 1 times c. OK, and so here's our Lagrangian L, right? If we take the gradient of L with respect to a, b, and c, we'll get the primal constraints, right? Gradient with respect to a is x, with respect to b is, well, minus y, with respect to c is x plus y minus 1 negated. But if we take it with respect to the primal variables, we'll get the dual constraints, right? So dl by dx is equal to, 2 minus a minus c, right? dl by dy is equal to 1 minus b minus c, right? And then because x is a free variable, these are equality constraints. So we set that equal to 0, and we set that equal to 0. And so we get a plus c equals 2 from this guy, and b plus c equals 1, right? So we're considering, right, we're considering all of these guys to be inequality constraints, right? And so there's no bound on the range of x, right? We could have, if we wanted to, introduced only one Lagrange multiplier for this non-trivial inequality constraint and considered these guys as bounds on the range of x and y. But I did it. It's actually usually easier to do it the other way. Think of x as a free variable and everything as non-trivial inequality constraints. OK? So we get those. And then we substitute these back into the Lagrangian, right? So 2 minus a minus c is 0 means that this term, and this term vanish. 1 minus b minus c is 0 means that this term, and this term vanish, right? And so we get, the only thing that's left is minus c times minus 1. And so we're going to get max c subject to all of those guys. And that's going to be the dual. Right? This is 0.
Can you please repeat the one part where you talked about the sign of a, because...
Right. So if you're doing it the Lagrangian way, you have to be able to build the Lagrangian. And the best way to think about it is that the Lagrangian, it's a game between the primal and dual player, right? So I'm trying to minimize the Lagrangian with respect to x and y and maximize it with respect to the dual variables a, b, and c, right? And so what I want to do is I want to put these extra terms, so the primal objective always goes in the Lagrangian, and then I put extra terms in the Lagrangian to try and enforce the constraints, right? And so, for example, if I want to enforce the constraint x plus y is greater than or equal to 1, or x plus y minus 1 is greater than or equal to 0. Well, so think about what happens if I violate that, right? So x plus y minus 1 is strictly less than 0, right? Then its negative is strictly greater than 0. And now the dual player, right, is controlling this Lagrange multiplier, has to be positive, and it's multiplying something positive. So what am I going to do as the dual player? I'm going to increase c to be something incredibly large, right? And the Lagrangian is going to go to plus infinity when I do that. So if I'm the min player, right, I don't want that to happen. So I darn well better satisfy this constraint to prevent the dual player from making me look stupid.
So we're trying to minimize the Lagrangian.
You try to minimize with respect to x and y, maximize with respect to a, b, and c, the Lagrangian of x, y, a, b, c, right? Or max min, right? One is the dual, the other is the primal. So question up there?
Yeah, can you just real quick write out how those things cancel out?
Right, so we can rewrite the Lagrangian as x times 2 minus a minus c, right? I've collected this term, and that term, plus y times 1 minus b minus c plus c, right? And so I just proved that in I just imposed these constraints in the dual, right? So this is 0, that's 0. These two terms vanish, and you're left only with C in the Lagrangian. Yeah?
Are there restrictions on the form of the initial problem, like it's not being standard or?
So no, so the question is, are there restrictions on the form of the program before you can dualize it? And the answer is no, but sometimes it's easier if you put it in standard form or inequality form before you do it, right? So for example, if you're writing software to do it, one of the first things the software might do is put it in standard form or into inequality form before trying to take the dual. Yeah?
So if the second constraint was x plus y is equal to 1, it's greater than or equal to 1, the
Right.
only difference would be that in the solution, there is no bound on C.
That's right. So then C here, C greater than 0 wouldn't happen. And yeah, everything else would be the same. Yeah, you had.
So if we have this type of question on an exam, and at what point do we solve this and then we say, okay, we're done? Like, what's our final step? We kind of like went.
Right. So here, right, the final step is that this is the dual, right? And the way so in this min-max the Lagrangian form, right, the way that you would know that you're done is you would carry out the minimization over the primal variables, get some constraints, and substitute those constraints in. And then once you've done that, you're done. There are cases, like on the machine, we did some additional manipulation after that. That's not technically part of the dual, right? So we formed the dual, and then we did some more manipulation to rearrange the dual, right? For example, to get rid of W. And that's not part of taking the dual, but we're not going to penalize you for simplifying the dual after you've taken it. Yeah?
So you're not saying that we have to write like the minimum value of x and y?
There's no way to do that unless you solve the problem, right? So we're not asking, when we're asking you to take the dual, right, we're specifically not asking you to solve the primal or dual linear program. If you do that, more power to you, but the dual ends at this point, right? So in a linear program, when you've eliminated all the primal variables, right? But in general, when you've, made these constraints and substituted them in.
How do we solve it?
How do we solve a linear program?
How do we, can we solve the dual? Do we have?
Let's see. So our official advice for solving linear programs has been give it to Simplex, right? So, but this one, right, is simple enough that we should be able to solve it, right? So, right, yeah, exactly. This is going to be the A and B will be 0, C will be 1, right? Just by inspecting. You want to make C as large as possible. That means we make B 0. There's no penalty for making B 0. We'll make, yeah. A will be 1, right, to be able to satisfy this constraint. So A is 1, B is 0, C is 1 is the solution of this one, right? And if you go back and look here, right, that'll mean that A and C will be the tight. So x bigger than 0 and x plus y bigger than 1, those will be the tight constraints in the primal.
Apart from inspection, there is no other way to solve it?
There are plenty of ways to solve it, right? So the simplex algorithm, there are projected gradient methods, there's interior point methods, but we aren't covering those in this course, so we're not going to ask you to simulate them on the exam, right? I mean, there's gradient descent, and we might manage to figure out some gradient descent question that winds up with you solving an LP, but it would be mostly a question about projected gradient descent. Yeah.
Does converting to dual always help in linear programming, or
Does what?
does converting to a dual always help in linear programming? Or?
Does converting to a dual always help in linear programming? No. Sometimes it's easier to think about the problem in the form. Sometimes it's easier to think in the form. Dual solution. Happens that you have a use for the no, right. So usually the way you find out is by trying to solve the dual for a while, right? And whichever one you finish first, you're done, right? Yeah. Oh.
Just 1 second.
Yeah. Okay.
Because I need.
Yeah, sure.
So, what was the intuition behind how you chose plus or minus? I sort of lost that.
Right. So in the Lagrangian form, the best way to choose plus or minus is you think of this game here, right? The primal players are trying to minimize the Lagrangian. The dual players are trying to maximize it, right? And so you think about which sign would cause the primal constraints to be enforced, right? And so the way you think about that is, well, suppose the primal constraints would be violated, right? What would the dual player do, right? And so here, with this sign, if the dual constraint is violated, this is going to be negative, so its negation is going to be positive. So I'm going to have c times something positive. And so if I'm the dual player, I'm going to be really happy. I'll send c to plus infinity, right? So if I'm the primal player, I won't do that, right? I'll make sure that this constraint is not violated, because otherwise the dual player is going to send the Lagrangian to plus infinity.
Okay. So almost like a cost function which includes A, B, and C.
So I'm sorry?
It's almost like the Lagrangian is a cost.
Right. So you can think of the Lagrangian as a cost function that's a function of both the primal and the variables, right? And it's player to minimize it, and it's a player because they're trying to maximize it, right? And so it's a sum game into game theory. Right? Yeah.
So assuming that the dual is handy, whatever method solves gives A, B, and C, that goes on Lagrangian and then we minimize it?
Oh, right. So in the case of linear programs, it's not necessarily trivial to get x and y if you know A, B, and C. But the way you would do it is by trying to solve the Kkt conditions, right? So you would use the Kkt conditions to figure out what constraints had to be tight. And hopefully that would give you a unique answer about which constraints had to be tight. And so if they're tight, they become equality constraints, and you'd solve a linear set of equations to get x and y, right? And in this case, that actually works, right? So if I remember right, it was A and C that were non-zero. So the tight constraints were you'd make x equals 0 and x plus y equals 1. You solve that for x and y, you get 0, 1. And that should be the answer to this one. Now, if you're unlucky, the Kkt conditions won't tell you uniquely what has to be tight. And then there's, you have to do some kind of a search. But the maybe a better answer is you use some software to solve the dual that gives you the primal variables for 3. Right? And if you want to know how that magic happens, take the optimization course. But if you do that, then you get both dual and primal at the same time. Yeah?
And how is the Lagrangian different if you start with a quadratic composition?
Right. So the Lagrangian will have a quadratic term if you start with a quadratic program.
But just from the original objective?
Just from the original objective, right? The way you handle the inequality constraints is exactly the same. And so what that'll wind up that the minimization looks a little bit different and the dual looks a little bit different, but you saw it a bunch of times in the support vector machine, right? So if you go through the support vector machine dualization, that's A, a good thing to study for the exam, and B, it shows you what's going to happen with the dualization of a quadratic program. Yeah.
It's a very practical question.
Yeah.
Does anyone solve these things anymore, or just give it to a software?
Oh, so for linear programs, for moderate-sized linear programs, just hand it to Simplex, right? It's still a research topic, the best way to solve certain kinds of other convex programs. And so people will often write purpose-built software, right? So the rule is usually that if you understand something about your problem that's difficult to communicate to Simplex, you'll be able to beat Simplex by doing something special purpose-built, right? But Simplex is usually a good place to start, and for most cases, it's a good place to end, but there are definitely research problems where that's not true.
Would we be doing some Simplex in this course?
We might at some point give you a homework assignment where we gave you linear programming software. It might be Simplex or something else, and ask you to do something with it. Yeah. All right. So can we leave this and go to the other interpretation, or is this?
So what again are the Kkt conditions?
The Kkt conditions, right. So for Kkt conditions are primal feasible, dual feasible, and objective values are equal, otherwise known as complementary slackness, right? So Kkt conditions here will be x and y are greater than or equal to 0, x plus y is greater than or equal to 1, right? Primal feasibility. Dual feasibility, a plus c equals, a plus c is equal to 2, b plus c is equal to 1, a, b, c all greater than or equal to 0, right? And then objective values are equal, so 2x plus y equals c. What's that? So, and then this equality of objective values, you can reformulate it to be the maybe more familiar complementary slackness condition, right? So, don't know if I can do that off the top of my head, right? But in general, what you
For Kkt, don't you also have that c times x plus y minus 1 equals 0?
So c times x plus y minus 1 is equal to 0.
Yes.
Right.
A-
So,
0, by equals 0.
right. So here, right, right. So it will be that, right? There'll also be ax is equal to 0 and by is equal to 0. And these guys should all follow from this, plus these guys, right? So let's see if I can derive one of them, right? So we know that a plus c is equal to 2, right? So we'll get, this is the same as saying a plus c x. B plus c is equal to 1 plus, so b plus c y is equal to c, right? And so now it should be that I can factor this, right, into, so we have ax plus by, right, plus c times x plus y minus 1, right? And that has to equal 0, right? And so each of these terms is non-negative because it's the product of two non-negative things, and therefore each individual term in the sum has to be 0 in order for this whole thing to be 0, right? So I find it easier to remember as objective values are equal, and then if you substitute in, the dual constraints, you'll get, and rearrange, you'll get this thing, right? So, but you get either, it'll be either this or this. You don't need both of them.
How did we get 2x plus y equal to c?
That was the primal objective value 2x plus y has to be equal to the dual objective value c. Right? Right, exactly. So if you go from the lower bound perspective, right? So every primal feasible point gives you an upper bound on the objective because you could always pick that as the optimal point, right? Every dual feasible bound gives you a lower bound on the objective. And so for them to, when they're equal, you must have an optimal primal point and an optimal dual point. Okay, so now we go to doing this the other way, right? So let's see if I can, this is min 2x plus y. X and y are greater than or equal to 0, and x plus y is greater than or equal to 1, right? And so what I want to do is form a lower bound on the objective, right? So I can, and I'll form it using linear combinations of the constraints. So I'll take a times x plus b times y plus c times x plus y minus 1, right? And that's going to be bigger than or equal to 0, right? And then I'll gather together all of the x terms, right? So I'll have a plus c x plus b plus c y minus c is greater than or equal to 0, right? And actually, I'll just move this over, right? So I'll be that's greater than or equal to c, because it doesn't have an x or a y in it. And so now here, this left-hand side, I'm going to set it equal to my objective, which means I'm going to match coefficients. So I get a plus c equals 2, b plus c equals the coefficient of y is 1, b plus c equals 1, right? And then if that's true, we have that 2x plus y is greater than or equal to c, right? And now I have the dual. I have the two dual equality constraints, and I knew that a, b, c all had to be bigger than or equal to 0 to make this thing true, right? And then c is going to be my lower bound, and so the dual will be to maximize that lower bound, right? And so these are actually doing essentially the same sequence of mathematical operations, but they're doing it with a different explanation attached to them, right? So for example, here, right, I took the coefficient of x, whereas in the previous one I took the derivative of the Lagrangian with respect to x, right? So the Lagrangian had this, and so the derivative was going to be this 2 and this a plus c, and setting that derivative to 0 was setting 2 equal to a plus c, right? So it's exactly the same sequence of mathematical operations. It's just that the reason you're doing them is slightly different, but equivalent.
So is there a different name for this strategy?
No, they're both called dualization. There's probably a dozen different ways to interpret dualization. And so people didn't bother coming up with different names for them. They're just sort of different ways to get intuition for what the dual means. I happen to like this lower bound strategy because it's much more difficult to get the signs wrong, right? And also, like, it sort of makes sense. It's good to get a lower bound, and I use constraints multiplied by some multipliers, right? And then, well, I have to make I have to make part of this bound equal to the objective, so I match coefficients. My lower bound.
Yeah, the only part that I get confused with this is I know that I need to minimize 2x plus y.
Mm-hmm.
When you express it as 2x plus y is greater than or equal to c,
Mm-hmm.
that intuitive that I need to maximize c and not minimize c.
Well, let's see. So each c gives you a lower bound, right? The best lower bounds are the tightest ones, right? In other words, if I tell you it's bigger than 1 or I tell you it's bigger than 5, which one is more information telling you it's bigger than 5, right? So I want to get the tightest lower bound, which means I have to maximize the lower bound. Are we starting to lose steam? Do people have more questions? Yeah.
In the questions that you got in homework, one, there's given draw the resistant boundary kind of questions.
Mm-hmm.
Should we always assume that they're not using any kernel? When you say what is the resistant boundary if you apply logistic regression or perceptron?
Right. So if we don't give you a kernel or a feature map or anything like that, you have to assume that the feature map is the identity, and therefore the kernel is just the Euclidean dot product.
Could you post the solutions to homework on the webpage?
Right. The TAs are working on the solutions as we speak, and we're hoping to post them very soon. Yes?
If you have a quadratic function and you have quadratic constraints, can you use those similar to this dual?
Right. So you can make a dual for any optimization problem with any kind of constraints. If the problem is non-convex, then the duality may not be so helpful, right? You might get a big duality gap. but you can always do it. It's not, we're not going to need it in this course, so we're not going to test that on the exam, but it's a good thing to know how to do in general.
The same sequence of steps.
It's the same sequence of steps, right. If you want an example, there's the typical textbook is this Boyd and Vandenberg convex programming textbook, and they go through some examples in excruciating detail. It's like an 800 or 1,000 page textbook. But you know, it's got a lot of examples of taking duals of things that are pretty crazy. Yeah.
So you said that these are equivalent, like once you take a derivative and once you just compare coefficients.
Right.
But that kind of works on the function is linear because then the coefficient becomes the derivative.
Right.
So what happens when like those constraints are quadratic?
Right. So you can use the same intuition for any convex program to do the duality. You can think of it either as lower bounding or as making a Lagrangian that's a zero-sum game. And you know, it gets more complicated for the other programs, but you can still push through both intuitions. I saw a question, a hand up there. Yeah.
Kind of a different topic, but for the probability section, is there a certain subset of distributions that you want us to make sure that we're on top of, or like all the distributions?
I would make sure, particularly to know Gaussian and multinomial, right? Those are the big ones. More obscure ones, we'd give you the PDF if we wanted you to work with them. Because in real life, if you wanted to work with them, you would Google it, get the Wikipedia page, and work from there, right? Yeah.
I'm still a little bit confused how we got from A plus C
Right. So what I wanted to do, so I got this step, right, is I get just some inequality that has to be satisfied when I take some non-zero, some positive, non-negative multiples of my constraints, right? And so I have this, and I want to get a bound on this, right? So how do I do that? Well, the only way to do it for all x and all y is to match coefficients, right? So I need to take the coefficient of x in this bound and match it to the coefficient of x in my objective, and take the coefficient of y in this bound and match it to the coefficient of y in my objective. And there's no other way to get a bound that's true for all x and y. Yeah.
About kernels. So if we had some feature map that created a different number of dimensions than was originally our data, how do we build a kernel that enforces that?
Right. So the question is, given a feature map, how do you get the kernel, right? And so you can make a slow algorithm for computing the kernel by enumerating all the features and taking the dot product. But of course, the hope is that you have a faster algorithm than that one for computing the kernel. And the answer for that is you have to get clever, right? So for each individual kernel, somebody wrote a paper where they said, oh, look, if you use this feature map, then there's an efficient way to calculate the kernel. Right? And so, you know, there's some crazy dynamic program that you solve to efficiently compute the substring overlap kernel, right? And that was a paper. And, you know, it was very early on that somebody noticed that polynomial kernels are efficient to compute, right? But there's no general answer. You just, you know, you look at it, you do the math ahead of time so that your algorithm doesn't have to do it. In most situations, you would pick an off-the-shelf kernel, right? I mean, there are situations where you'd come up with some new intuition about your data and design a kernel to take advantage of that. But at this point, there have been enough people who have written enough papers of that form that it's probably a lot easier to go find the, you know, ICML 97 paper where somebody wrote about, you know, foobar kernels and, you know, pull that one and cite it. Yeah.
Related to kernel, if I have a feature that's x squared x cubed,
Mm-hmm.
and then I use a quadratic kernel on it, if you use those and highlight what savings would be computationally.
So you start off with x, you manually turn it into x squared x cubed, and then you do a polynomial kernel of degree 2 on top of that. So you could get up to 6th order polynomials that way. Right? I'm not really sure. I can't think of a benefit of doing it that way, right? Like you could just do, well, OK, here's a benefit. So you could get 6th order kernels just by starting with x and doing x plus 1 to the 6, right? Or x times y plus 1 to the 6, right? And that would give you, that gives you all polynomial decision boundaries up to degree 6. But it gives you a very specific way of setting the coefficients in your feature map, right? They have to be the binomial coefficients.
I'm not sure I quite follow the x plus 1.
Right. So we showed you in class, right, that if you want to get a dth order polynomial kernel, right, you can compute, right, x dot y plus 1 to the d, right? And that's the efficient way of computing the dth order polynomial kernel. And this is equivalent to taking x and mapping it up to all possible dth order functions of x, and y up to all possible dth order functions of y, and then taking the dot product weighted somehow. And the weights in this case happen to be the binomial coefficients. We didn't prove that, I don't think. But if you wanted the weights to be something else other than the binomial coefficients, then you could do part of it yourself, right? Map it up to 3rd order yourself, change the weighting of the different terms, and then use the kernel to map it up higher. So that's kind of a, esoteric advantage, and I haven't ever seen anybody do this, but you could in principle.
I think in the homework, they didn't add 1. They just used
Right, so this polynomial kernel, there's the homogeneous, the inhomogeneous. This is the one. It gives you everything up to degree 6, including 0, 1, 2, 3, 4, and 5. Right? The homogeneous one gives you only degree 6. So you have like x1 to the 2nd times x2 to the 4th, but you wouldn't have x1 to the 2nd times x2 to the 3rd, because that's only 5th order. Right? So they're homogeneous one. And if one, then you should discuss.
Do you know what a phi looks like?
Phi looks like for which?
For the kernel.
Right. No, that right. So lower dimension feature map.
So in the version, if you were creating a D feature map, you would be doing D times D plus, or D squared calculation.
Right. So how many monomials are there of degree D? Right. Well, so you choose 6 things with repetition, so it's the dimension to the 6th for the homogeneous one, right? And for the inhomogeneous one, it's that sums over, 0 through 6.
For a kernelized one, when you're making the dot product, it's only D calculation.
That's right. It's you take D multiplications, D additions, and 1 power, right? So it's for D 100, right? It's just ridiculously more efficient to do it the kernel way than it is to do it the.
So 10 squared compared to n.
No, it's order n compared to exponential in n. Or D compared to exponential in D if the dimension is D, right? Yeah.
Could you clarify quickly, homework 2 solutions will be posted before, in addition to homework 1 solutions will be posted before the test?
Homework 1 solutions will definitely be posted. The homework 2 solutions, the TAs will do the best that they can. And they know that you want to see them and they're trying really hard.
Okay, in that case, there's a small question from the homework that I'm very curious about.
Yeah.
We were given 2 functions. One was x squared plus x to the 4th, and we were asked to show that it was convex. And the other was x squared plus x to the 4th over the integral 1 to 5.
Yep.
And we were asked to show whether that was strictly or strongly normally convex.
Right.
What is the difference between those?
The difference between So the difference between strictly and strongly convex, or the difference between convex over the whole?
It was the same function, but one was over, all reals, and one was over 1 to 5.
Right, and do you remember, was it strictly or strongly convex that they were asking about?
We were asked to show whether it was convex, strictly convex, or strongly convex.
Right, right. So,
So we're trying to figure if there's anything special about putting it in
right.
that interval.
Right, so let's take the Hessian, right? So it was, what was it, x to the 4th plus x squared, right? So the first derivative is 4x cubed plus 2x. The second derivative is 12x squared plus 2, right? And so in this particular case, right, this is bounded away from 0 over the whole real line. And so it's going to be strongly convex on the whole real line. And it's also going to be strongly convex on every subinterval of the real line.
So that was just screwing with us.
You get different strongly convex.
Oh, right, you get a different strong convexity parameter over the two. Yeah. So it wasn't completely just screwing with you. So the strong convexity parameter is, right, so this is 24 times x squared over 2, right? And so it's a question of what multiple of x squared over 2 can you subtract, right? And so over the whole real line, you can only subtract 24 times this. But if you're over a limited interval, this 2 gives you some slack, and you can subtract a bit more, right? Yeah.
Isn't M, were you talking about M?
The modulus of strong convexity,
Yeah.
right?
Yeah. So isn't like the second derivative has to be greater than a certain quantity, and in this case it's like 14 because it's always greater than 14.
Right. Yes.
So M 14 to infinity.
Yeah, like it's at least 14, and but I didn't quite follow what you with 20.
Sorry. So I forget whether we defined the modulus of strong convexity to be adding a multiple of x squared or of x squared over 2, right? I was going with x squared over 2, but do you guys remember what we defined? It doesn't actually matter what the...
I think if we're looking for a lower bound of the double prime, in the first problem, the modulus of n equals 2. The second problem is the inverse from 1 to 5, then it's modulus 14. The lower bound is 14.
So, okay, so we must have used then just without the over 2. So, right, yes, right. So here, right, ignore all of this. Here, this is always bigger than or equal to 14, right? And over some interval, it might be bigger than something bigger than 14, right, depending on what.
No, in the interval 1 to 5.
In the interval 1 to 5, it's bigger than 14, right? And this is always bigger than 2 over the whole real line. Yeah, sorry. Yeah. Yeah. Linear regression with L1 regularization. What about it?
Intuitively, how does it bring the weights to 0?
Right. So intuitively, how does it bring the weights to 0? So there's the way I like to think about it, right? So let's think about, instead of the L1 penalty, make a constraint on the L1 norm. So that's like a diamond-shaped constraint on your weight vector, right? That's what the contour of an L1 norm looks like. And so now we're minimizing some quadratic, right? So let's, think about the center of that quadratic is somewhere at some arbitrary location on the page, right? So if the center of the quadratic is, here, right? Let's, for simplicity, let's suppose it's like that, right? It's circular. Then the minimum will be here, and both variables will be non-zero, right? And that's going to be true if the center of the quadratic is anywhere in this region, right? Same with this region, right? And this region. And this region. It'll be both variables non-zero. If the quadratic is here, though, if the center is somewhere here, you're going to have one variable 0, right? And so if you think about it, now zoom out, right? That is going to be some tiny thin bars of an x, and the rest of L2, right, is going to be places where you get a sparse answer. So, you know, how lucky do you have to be to land right on one of the bars of the x? That's not a fully rigorous explanation, but it's a good intuition for what's happening. Can I also explain L2 regularization? What about L2 regularization? Right, so with L2, it wouldn't be a diamond, right? It would be a ball that you'd be constraining to. And so no matter where your minimum is, you know, you'd have to be incredibly lucky to get a 0 answer, right? You'd have to be like on the positive real axis to get a, right? And so it's the reverse situation. You have to be lucky to get something 0 as opposed to be lucky to get non-zero. Yeah?
I don't quite follow the diamond of the goal.
So suppose we're doing the following optimization, right? Minimize x minus x0 quantity squared subject to the norm of x, one norm is less than or equal to c, right? So this isn't quite the lasso, but it's a simplified version that's like the lasso, right? So it's got a constraint instead of a penalty, and it's got a spherical quadratic instead of the, you know, not quite spherical quadratic that you would get in a lasso, right? And x0 here is your problem data, right? And so the question is, when are you going to get a sparse answer? Well, it's going to depend only on where x0 lands, right? And so if x0 can land anywhere in the plane, suppose it happens to land here, well, then your answer will be here, and you'll get two non-zero components, right? This is like 1, 1 is your answer here, right? If this is, suppose this is 2, 0, this is 0, 2, right? And so this here will be 1, 1, right? If you land right here, that's where the minimum occurs, right? And so the question is, so if you land anywhere in this, in this bar, right? Well, going out and in doesn't make a difference. Going left and right will move the minimum back and forth, but it won't make anything 0 until you go across this dotted line, right? And then here, one of the components will be 0 until you cross this other dotted line. Right? And so the point is that these bars don't take up very much space compared to these huge wedges. And that's the intuition for why you usually get some 0 components. Stochastic gradient descent, we could ask you a question about stochastic gradient descent on the test.
Also about novelty detection.
Novelty detection, that's not on the list of topics, right? So we shouldn't ask you a question about that. We could ask you something that was tangentially related to novelty detection, but it would be mainly about one of the other questions.
So basically, what was the lecture today will not be on the test.
What's that?
Today's lecture is not be on the test.
Today's lecture, I really don't like to say a lecture is not on the test, right? Because the concepts covered in the lecture overlap with the concepts covered in previous lectures, right? So, but novelty detection, there will not be a question that is primarily about novelty detection on the test, right? But there might be something that's tangentially related to novelty detection, right? But we're not trying to test novelty detection. We're testing something else with that. Yeah?
So when Alex was talking about Newton's method, he took a second-order Taylor approximation using a Hessian matrix and a gradient matrix.
Yep.
What are the dimensionalities of these matrices, or what are the dimensions of them?
Right. So in Newton's method, let's give us a problem for Newton's method, right? So we want to say minimize f of x, right? And x will be some vector in Rd, right? And so f will go from Rd to R, right? F will do that, right? And so the gradient, right, it'll be, so f prime is a function which goes from Rd to RD, right? It gives you put in an x, and you get the gradient with respect to x, which is a vector of length d, right? And then f double prime, you'll take in an x again, and it will go to our d cross d, right? It'll be a d by d matrix. All right. Are we all tired? Hungry, yes. Tired and hungry. All right, that's a good reason to stop. All right, good luck on the midterm, guys, and see you on Monday. Oh, you're welcome.